Hi everyone, welcome back to Stats. So today we're going to be talking about how to analyze discrete data. So this is data where everything is put into categories. You can't put anything on a continuum. So I'm first going to talk about the chi-square analysis. I'm going to be running through a longer version of it through R as if we were going to manually calculate every part of a chi-squared analysis. I'll then go through a few different examples of chi-square analyses. And then at the end of all of this, I'm going to go through the example I was talking about in the last lecture, and we're actually going to do an analysis to see if Raja actually eats his food better when I'm not here than when I am here. So I'm going to have some made-up data that I'm going to analyze to test that. We'll walk through those examples. So with that, let's jump in and look at how chi-square analysis works. All right, so let's jump into an example of how you conduct a chi-square analysis in R. So I'm going to load up the LSR package because we're going to be using that for some of the functions we're going to use. I'm also going to grab a data set called randomness.rdata that came with the textbook, and that contains 200 observations of some random card draws. So let's run this and take a look at what that looks like. So you'll remember the head function just grabs the first few rows in the data set. And you'll see here that there is a variable for ID. And then there are two different variables for card draws here. So when you're doing a chi-square analysis, the first thing that you're going to want to do is, rather than having that regular vector, you're going to want to convert this into a table. So when we run this, we'll have a table for choice 1. And so if I print that out, what you'll see down here is that now it's made a table for clubs, diamonds, hearts, and spades. And what we can do is we can compare that to probability based on random chance. So for this, I'll just drop this down here before I run it. So we're creating probabilities where clubs is 0.25, diamonds is 0.25, hearts is 0.25, and spades is 0.25. So this is the first step that we're taking. And again, this is just a regular vector to start off with. And what we're going to do is multiply that by the sample size. So I'm going to create a sample size of 200 here. And so what I'll be putting here is the expected frequencies. So expected frequency is what we would assume based on maybe random chance or based on something that we know about the population. So for this, you're getting the expected frequency table. And then if we look down here, what we have is if you had the same amount of cards, 200 cards, by random chance, you would expect to have 50 of each of the 4 suits. So then what we can do here is we can manually run a chi-squared test called the chi-square goodness of fit test. And so this is comparing, how different is our observed result from what we would expect just by random chance. And is that so unlikely that we think that it's unlikely enough to be due to chance that it is statistically significant? So the first thing that I'm going to do is see how different each of those cells are. So if you run observed minus expected, you see that you're going to be getting minus 15 for clubs because there were 35 clubs rather than 50, and the same thing happens for all 4 of those suits. We're going to be getting the squared deviation here. You might recall this from earlier in the class when we talked about squared deviations. And so with this, it's going to be giving us a 225 for this because it's taking minus 15 and multiplying it by itself. And you get all of these other deviation scores as well. And so what you then do is you divide that by what you're expecting by each of the cells. So this is the sum of squared deviation divided by the expected value. So that's the next step in a chi-square analysis. And then finally, what you do is that you sum up all of those scores. So it's adding 4.5, 0.202, 3.92, and 0 for this, because there's exactly as many speeds as we expected by chance. And so this gives us a chi-squared goodness of fit test. So what this is telling us is the larger this score is, the further away the observed values are from the expected values. So the further away they are than what we would have expected just by chance. Basically, larger the chi-square value, the lower probability that would have happened just by random chance, assuming that we had a deck of cards that was a fair deck of cards. So then from here, what we can do is compare our chi-squared value to what we would expect by random chance based on the chi-squared distribution. So first of all, let's put this down here. And what we find is this value of 7.814728. And so what that is that is our cutoff value for deciding whether or not our chi-square value is statistically significant or not. So 8.44 is larger than 7.814728, and so that seems to be unlikely due to random chance. So for the p-value, this is 0.95, and so this is basically setting the range that we would expect by random chance. So it's basically anything that is in the 5% most extreme would be considered statistically significant. The degrees of freedom here are 3 because we have 4 groups. For example, if we had 5 groups, there would be 4 degrees of freedom. All right, so then what we can do is we can put in our actual value and see what is the p-value for our observed chi-square score. So you put in the actual chi-square value and the degrees of freedom. For this, you can specify lower tail equals false, because the default for p-values is to get the lower tail, so everything below a cutoff point. But for chi-square, anything that's higher is statistically significant, so we actually wanted to do the opposite of that. And so here you have a p-value of 0.0377, etc. So that is less than 0.05, which makes sense because it's beyond that cutoff point. So another way that you could run it, which is maybe less intuitive, is that you can basically get the opposite of the p-value by just letting it do the lower tail and then subtracting 1 from that. So essentially what that is going to be the same value, because if we had left it at the default of lower tail, it would have given us this p-value of 0.96. So by random chance, essentially 96% of the time, roughly, you're going to get a chi-squared value below 8.44, and only about 4% of the time you would get a chi-square value of 8.44 or more extreme. That means higher than 8.44. So these two functions are actually just doing basically the same thing. All right, so because it's in that critical range beyond our cutoff point that we have decided based on our alpha level and our degrees of freedom, we'd say that our observed cards are beyond what we would expect by random chance. And again, that's basically saying the 5% most extreme outcomes are considered statistically significant. All right, so we've done it the long way, going through all of those individual steps ourselves. But what we'll also want to do is run those analyses with functions that we already have in R, which is what I'll be doing next.